Hey everybody, welcome to week 7 of PS 398. Oh boy, I haven't recorded you guys second in a while. Time for some fluids. Regardless, I hope that you are less tired than my voice. Just keep going. You're doing such a great job. This is a hard class, and you're getting so many different things from so many different angles. It's not always easy to keep track. It's hard to know when something is difficult versus when something is new versus when something is tedious versus when something is stupid. You know, it's hard to know. Sometimes you just know that you don't understand something or that something doesn't make sense to you. There's lots of reasons that something might not make sense to you. And I think I've been showing you things that might not make sense for lots of different reasons. And that can be taxing. And I'm sorry about that. Unfortunately, this is just material that lends itself to a lot of confusion, but I think one thing that I've noticed from you all is that you're starting to have useful confusion. You're starting to be wrong though in helpful ways. And I know that sounds so patronizing, but when you learn a language, for those of you that learned other languages, I'm so bad at languages. Like, there's a stage where all you do is screw up. I'm trying to speak Spanish to you, and everything I say is wrong. I use the wrong words, or I violate syntax, and I don't know that. I need some helpful and patient teacher to tell me when I said biblioteca when I should have said something that sounded like biblioteca. But then comes a phase where you still screw up all the time. You still screw up. This is important. You still screw up all the time, but you start to notice your screw-ups as you're making them. And you kind of say, biblioteca, never mind. Like, you know, you still make the mistake. Your instinct was wrong. But then some part of you kicks in and says, oh no, whenever you were wrong, and I'm going to be the censor this time. I don't need the kindly teacher anymore. And that's a really important phase of learning a language. And from what I've gathered, several of you are at a similar point with this class to where, yeah, you're wrong sometimes, but you're also noticing when you're wrong, and you're better at asking me questions because you're wrong in useful ways. You know, there's all sorts of different ways to be wrong. And of course, several of you are also just wrong less frequently than you were too, which is great. That's what we're going for. More importantly, the substantive questions that I've been getting have been spectacular, where it hasn't just been, oh, well, help me to calculate this expected utility, but also, what does expected utility mean, and when would I use it right now? It makes me really happy. It makes this really rewarding. You know, I haven't been shy about sharing how I'm feeling with all of you, and I'm sorry about that. Sometimes I'm sure it's weird, but it makes this all worth it. You know, and I'm just so grateful for that. And so, you know, it's selfish of me to say, but please keep doing what you're doing. I'm so lucky to have all of you as my students. And you might think I'm only talking about a couple of you or something, and I can't claim to know every one of you personally, right? But it's been more than just one or two. Sorry, now I'm tearing up. I don't know. I don't want to finish this thought too much because then I'll just start crying, but just keep going. I'm so pleased to watch you learn. It kind of sounds vain, but I don't mean it that way. It's a pleasant thought that I can help you learn. So anyway, thanks. While we're issuing thank yous, could everybody just please say, hey, Lucy, thank you so much for being such a wonderful grader and for helping me with all of the questions that I didn't want to bother the fat man with. Lucy's been doing a great job too. So we're all just so darn lucky, except for you, you're stuck with me. So we're finally at the point to analyze a game. This is a class about how to use game theory to understand what countries do. And the first few weeks are just basically how to use game theory to talk about countries. How to use game theory to talk about decision makers. How to use game theory to think about all sorts of various international processes, but not to talk about what actually happens. We haven't talked at all about what happens. We have issued no behavioral hypotheses beyond any given decision maker has enough consistency in their decision-making structure that we could assign utility numbers to their preference rankings, right? That's the only assumption that we've made about behavior so far. We haven't really said, and here's how that all plays out. So today is the week where it finally has come time for us to talk about what countries do, what actors do, what leaders do. How does this all play out? What's the ending of the story? How do we get from a fable that we've written, which is a set of players, a set of actions that they can choose, and their preferences over those outcomes? How do we take those three things and then turn them into a what happens? Conditional on who they are, what they can do, and what do they want? And so that's Nash equilibrium, among other things. We talked a little bit about IESTS and how it can help us to make predictions, but it also only has so much bite. The thing that makes it so intuitively appealing, the strict dominance thing, also happens infrequently enough that oftentimes an analysis with IESTS doesn't really get off the ground. So we need something that will get off the ground a little bit more often. And that's Nash equilibrium. Nash equilibrium strikes a very nice balance between it's very reliable, it will always give you a prediction, and it narrows things down, which is what we're looking for. So Nash equilibrium is a very famous concept. It is the core analysis concept in all of game theory. Without Nash equilibrium, there wouldn't be much for me to show you, much like expected utility. So this basically says, let me exploit everything I can about expected utility and use that exploitation of the analytic structure of expected utility to generate predictions. And it's going to take several weeks for me to show you just how much we exploit expected utility and all that's in there. Today, I just want to introduce the underlying fundamental logic of Nash equilibrium. Just by way of history, Nash equilibrium is named for the mathematician John Nash, who was at the height of his powers in the middle of the 20th century. I think he was an early 1940s PhD from the mathematics department at Princeton. John Nash is himself an interesting character worthy of learning a lot about himself. I will post a couple of things on Piazza about the interesting wrinkles in John Nash's life. If you may have seen a movie, it was made in 2000 or 2001. It's called A Beautiful Mind. It is based on Sylvia Nasser's biography of him of the same name. It won Best Picture. I think it won Best Picture. It did win Best Picture, which is evidence of how weak the movies were that year. It's a good movie. It's not a great movie. No disrespect intended to Ron Howard, its director. It also got a lot of the math wrong. John Nash won a Nobel Prize in economics for what he contributed to game theory, but his main work was in pure mathematics that wasn't especially applicable and that we're still trying to understand some of the things that he did in the 50s in terms of the relationship between analysis and geometry and partial differential equations. His work was some of that work that you see it, or mathematicians saw it at the time and they knew it was great, but they didn't quite know what to make of it. He did not invent the concept of Nash equilibrium. The concept of Nash equilibrium dates back at least to the 1830s when the underlying idea of no deviation that we're going to be talking about today, that concept dates back at least to a study from Augustin Cournot, who was trying to study how two firms would choose a price in response to one another if they were the only two firms in a given sector. So if they could set the prices and didn't have to operate under perfect competition, but there was enough competition between the two of them that they had to think about one another's decisions. That sounds very game theoretic, right? And so it turns out that Cournot's model of oligopoly, it's called, that model really set the stage for what is now Nash equilibrium analysis. It's just that the underlying mathematics weren't quite ready for that just yet. And two, we didn't know when there was an equilibrium. John Nash, the reason that his name was attributed to Nash equilibrium is that he encoded Cournot's logic just right. And then conditional on that just right encoding that he came up with, that John Nash came up with of Cournot's logic, he was able to prove that Nash equilibria existed in a large class of games, so that we never had no prediction. We might have multiple predictions, but we'll never show up with no predictions. So my goal for today is for us to talk for 2/3 of the time about the vanilla, the basic version of Nash equilibrium, the introductory, intuitive version of Nash equilibrium, that of pure strategy Nash equilibrium, and then the C block will nod a little bit toward the future so that we're ready for mixed strategy Nash equilibrium, which we'll discuss next week. So this will be a 2-part lecture, with apologies for a boring introduction next week. Not that this one was exciting. But this is officially us getting down to brass tacks. We are officially going to begin the analysis part of this class. And so we'll switch back to the art of modeling and how to come up with cool models later, but in order for us to really get the most out of those models, we need to think hard for 2 weeks about how to analyze a game in the style of Nash. So that's what I want to do today. In the A block, I will define the concept of Nash equilibrium. I will show you what is and what is not a Nash equilibrium in a variety of games, and we will talk about the real definition of Nash equilibrium. In the B block, we will talk about best response correspondences, which are a way of simplifying the analysis. One annoying thing about Nash equilibrium in its default setting definitional sense is you have to check a lot of different things. It's really annoying from a computational standpoint to have to check so many things all the time. Best response, which we'll talk about in the B block, helps to simplify that, while also introducing a very important substantive aspect that is especially relevant for international relations. The idea of best response is that I come up with a function that reads in my expectations of what you will do and spits out what is best for me. So if I think that you're going to attack me on the Western Front, what is my best response? If I think you're going to attack me on the Eastern Front, what is my best response? So basically, best response is a matter of thinking through all of the other players' contingencies and saying, what would I do? What would I do? What would I do? And then we think about Nash equilibrium as what happens if everybody is doing what they would do to everybody else doing what they were doing. And you're like, that sounds stupid. It kind of is, it kind of isn't. You'll see. And then the C block, I want to talk about probabilistic strategy. I want to talk about how we think about expected utility in the games that we've been discussing up to this point. Right now, everything has been very just so. Everything has been very certain. But it turns out that a lot of the beauty of game theory and a lot of the utility of the most powerful tools like Nash equilibrium relies on us being able to come up with a probabilistic structure to impose upon a game. To say, I'm going to play heads 2/3 of the time and tails 1/3 of the time. I'm going to defect 20% of the time. Or whatever the case may be, so that it isn't just a matter of choosing some discrete choice. It's not just a matter of saying, I defected, that's what I do. Now there's a little bit more nuance, there's a little bit more wrinkle, which seems to play out in terms of how countries interact with one another in international relations. So my goal for you today is to go from somebody that can appreciate some of the beauty of these wonderful fables, which are gorgeous, spectacular ends in themselves, but I'm ready for you to start poking at them. I'm ready for you to start analyzing them. It's time for us to say, here's a game, and what's the ending? But rather remarkably, a lecture which is entirely oriented about how to tell the ending of fables has to have a beginning. Let's get started. Okay, so I'm going to introduce Nash equilibrium first by way of example, and then we'll come up with some formal definitions. But I think this is easiest to describe the logic in the context of a particular example. And so you know 5 games up to this point, so let me just choose one randomly. Let's play chicken. I already noted to my other class that there was just a huge missed opportunity last week. You know, I have this cool game on the screen, but the thing that I really want to convey is just how much command I have over that game. So, now you don't see it. Now you see it. Now you don't. Now you see it. Now you don't. We probably should land on a spot where you can see it, right? Now you see it. I got to keep myself entertained somehow. You try filming 9 hours of lectures in one Sunday afternoon and don't turn loopy at the end. All right, so here's chicken. And we already said that chicken is an interesting model that helps us to learn about nuclear brinkmanship, nuclear crises. So on your problem set, you even said, these war payoffs, you know, there's these crises payoffs, there's a nuclear war option, there's all these different things at work, but I just want to talk about the simplest version of chicken that we talked about last week's lecture. So let's think through profile by profile. I want to look at each action profile and say, does this seem like a landing spot? I want the logic of landing spots to be in your head. I want you to be thinking about, does this seem like a stable outcome? Okay. What do I mean by stable outcome? I mean, is it going to be true that in a given profile, once you've learned what everybody else does, which in a 2-player game is just learning what the other player did, once you've learned that, Do you wish that you would behave differently? That's the basic underlying idea here, is at a given profile, not only have I done something in a profile, maybe I went straight or maybe I swerved, either way, I learned that you did something too. And conditional on what you did, do I wish that I had done differently? And if not, for everybody, then that's an equilibrium. What do I mean by that? Let's start in the northwest corner. So this is the profile where we both swerved. I'm getting 1 happiness point and you're getting 1 happiness point. Okay? So we both swerved. We both said, no nuclear crisis. We back down. Status quo. So think about that. Well, if I knew that you were going to swerve, which is to say, if I knew that I'm going to be role player throughout today. So if I knew that we were going to be in the column where you swerved, your column player, if I had known that you were going to swerve, I could get 1 for swerving, or if I had gone straight, which is a counterfactual right now. That's a counterfactual. If I had gone straight, I would have gotten 2 against your swerve. I would have won. I would have looked really awesome. So I have a profitable deviation from this profile. So from this profile, I could change my mind and do strictly better. I could go from 1 happiness point from swerve to 2 happiness points for straight swerve. I liked playing straight against swerving. Consequently, because at least one of us has an incentive to deviate, because at least one of us has a profitable unilateral deviation, which is to say, hold everybody else fixed, could I change my mind from this profile and do strictly better? Because I could say yes to that, this is not a pure strategy Nash equilibrium. You'll see why I'm saying pure strategy next week. I'm going to say it every time, and for a week, you're not going to know why you're saying it or why I'm saying it. And I'm sorry about that, and you'll understand this all next week. I wish that there was just a way that I could inject everything into your head immediately, and you're like, not as much as I do, fat man. I don't want to hear your voice for 15 weeks. Notice, just for completeness sake, that you also had a profitable deviation. Let's suppose that we were staying in the swerve row. That's the row where I swerve. Well, right now, you're swerving and getting 1 happiness point. If you deviated, if you went, instead of swerving, if you had gone straight, you would have gotten 2 happiness points, which is better than the 1 that you're getting. So you have a profitable unilateral deviation as well. We don't need it to be both, but in this case it is both. So I can put a little X through that. That's not a prediction. In this model, with this solution concept, with this analysis concept, swerve is not an equilibrium. It's not a prediction. We don't think that's what's going to happen. Right? Our prediction is not that. We're officially ruling things out. We're officially getting to the bottom of it. It's time. We're analyzing. We're analysts now. Okay, well, that's 1 profile down. We need to check all 4 of these. We need to check to see if any of these profiles has this stability condition that sort of, oh, well, nobody has an incentive to deviate. So let's move down. Let's go to the one where I went straight and you swerved. So this is the southwest corner. So right now I'm getting 2 happiness points for being the winner of the game and you're getting 0 for being the chicken. Okay? Well, let's think about whether either of us has a profitable unilateral deviation. So let's start with role player. So I'm getting 2 happiness points right now. I'm getting 2 happiness points because I won the game. I went straight while you swerved. If I deviated and swerved while you swerved, then the game would have been a tie. We would have each been half a chicken. I'd go from 2 happiness points to 1 happiness point. I don't want to do that. I don't have a profitable deviation. Right? I won. 2 is the strictly best I could do. This is great. No, I don't want to deviate. This is great. But do you want to deviate? Well, right now you're getting 0 happiness points. So you're the chicken. Everybody's laughing at you. You may have just lost a significant other. You may have peed yourself a little bit. You know, you're the bad guy in a movie. So presumably, do you have an incentive to deviate? Well, let's think about it. Right now, you're getting 0 happiness points because you swerved while I went straight. Well, conditional on me going straight, do you wish that you had gone straight and died in a fiery car crash? No. -1 is strictly less than 0. You don't have a profitable deviation. So I don't want to deviate because I would go from winning to being half a chicken. And you don't want to deviate because you would be going from being a whole chicken to being a burned chicken. This is a pure strategy Nash equilibrium. this is one of our predictions. Or this might be our only prediction. But as of right now, we're saying this is past the test of pure strategy Nash equilibrium. Nobody has an incentive to unilaterally deviate. So that's a prediction. That's a prediction from this model. We're saying that one of the feasible outcomes, and you'll see there are several, or multiple anyway. One of the feasible outcomes of this model is I go straight and you swerve. Well, let's go up to the profile where I swerved and you went straight. Right now it's 0-2 in terms of the utility imputations. Well, do I want to deviate? Right now I'm the chicken. I'm getting 0 happiness points. That's no good, right? But if I deviated, conditional on you going straight, if I deviated, I'd be going from 0 happiness points to -1 happiness points. We'd have crashed. That's no good. I don't want to deviate. And right now you're getting 2 happiness points. If you decided to swerve, you'd be getting 1 happiness point. That's no profitable deviation for either of us. So maybe predictably, given the analysis of the last one, both straight swerve and swerve straight are pure strategy Nash equilibria of this game. So I'll just highlight them. Finally, let's consider the straight one. Well, right now we're both getting -1, which is our utility number for really grim death. See, -1 is just a lot more pleasant to talk about. So if we deviated, well, conditional on you going straight, if I went from going straight to swerving, I would be the chicken, which is better than dying. So I'd go from -1, I go from -1 up to 0. That sounds better for me. So I want to deviate. This isn't an equilibrium. Notice also that you want to deviate. You could go from -1 to 0. We both wish we could deviate. So this profile isn't a stable profile, right? So we have 2 X's. We ruled out the straight and the swerve. And what we said is the equilibria of this game, the pure strategy Nash equilibria of this game, are the 2 outcomes where there's a pure winner and a pure loser. Think about that in terms of the nuclear crisis thing. What that means is that if a nuclear crisis can be modeled as if it's a game of chicken, then our predicted outcomes, as of right now, there will be more next week, but as of right now, our predictions in terms of pure strategy Nash equilibria are there will be a winner and there will be a loser. Now, we can't tell you which, right? What do I mean? I mean that both of the winner-loser profiles, straight swerve and swerve straight, I'm a winner, you're a loser. I'm a winner, you're a winner. We're all winners, except there's losers. Both of those profiles pass this pure strategy Nash equilibrium test. So we can't really say which one. There's no reason for us to privilege one over the other. This will be a point I want to hit pretty hard in just a moment here. So this is a game with multiple pure strategy Nash equilibria. Many games have multiple, some games have unique. It's really nice when they're unique because then we know that's necessary and sufficient. That's our prediction. Here, we're saying being a pure strategy Nash equilibrium can only be a necessary condition for being a prediction because I have no way to say which of these is more sensible to me. They're basically the same equilibrium, except that in one, the person with the happy hat is me, and in one, the person with the happy hat is you. Apparently, the happy hat is what happens after you win the game of chicken, is you get a happy hat. Oh, I gotta start scripting these. So that's a pure strategy Nash equilibrium. So I want to talk about this multiplicity thing for a second, because it's really interesting. So let's switch from chicken to coordination, just so I can make this point a little bit more easily. I love that. The weird thing is, I mean, I'm not going to add that until I'm making the movie. So right now, I'm just doing this in air. I feel like I'm really cool because I'm just. But in reality, I'm just some moron in his office doing this. So here's the coordination game. Choose a 5G network, metric or SI, or literally drive on the left side of the road or drive on the right side of the road. Let's stick with that one. So let's check to see which are the stable profiles and which aren't the stable profiles. So let's start with left. Well, left, I'm getting a happiness point and you're getting a happiness point. Conditional on you going left, if I switched from left to right, I'd go from 1 to 0, no deviation. I don't want to deviate. And conditional on me going left, if you switch to right, you'd go from 1 to 0 as well. You don't want to deviate. That's a Nash equilibrium. That's a pure strategy Nash equilibrium. The same goes for right. So at right, conditional on you going right, if I switched to left, I'd go from 1 to 0. That's no good. And conditional on me going right, if you switched from right to left, you go from 1 to 0. That's no good either. So neither of us has a profitable deviation from right. So left, pure strategy Nash equilibrium. Right, pure strategy Nash equilibrium. Pretty good. Left, right, that's this one. Well, right now we're both getting 0. Well, conditional on you going right, if I had gone right, I'd go from 0 to 1. That's better. So I have an incentive to deviate. So too do you. Well, conditional on me going left, if you switched from right to left, you'd go from 0 to 1. That's better. So this isn't a pure strategy Nash equilibrium. Left-right is not a pure strategy Nash equilibrium because at least one of us has an incentive to deviate. We could do strictly better if we deviated. At least one of us, in this case, both of us. And the same goes for the right-left profile. So this game has two pure strategy Nash equilibria, the one where we drive on the left and the one where we drive on the right. So we've ruled out 2 options and we've left 2, which is somewhat frustrating because, again, substantively speaking, all that we can say is that it's an equilibrium thing for us to not crash into one another. If we crash, then we wish we had deviated. But who's to say how we choose which of these equilibria to play, the left one or the right one? Because if I start driving on the right side because I think we're playing the right equilibrium, and you start driving on the left side because you think we're playing the left equilibrium, next thing you know, we're in a car crash. What gives? So how do we know which equilibrium is the equilibrium that we're playing? Because there's multiple. There's multiple equilibria. How do we know which equilibrium is the right equilibrium? Well, let's think about that. Let's just observe that in the United States, we drive on the right. We play the right equilibrium, where I drive on the right and you drive on the right. Pause the video. Pause the video and think deeply. Give it at least 90 seconds. Think. Why do we drive on the right side of the road when it's an equilibrium for us to both drive on the left side of the road? What's so special about the right side of the road? Why do every day we wake up, every day people wake up all throughout the United States and they drive on the right side of the road? Even though that's no more equilibrium-y, that's no more equilibrium-y than for them to wake up and drive on the left. So why do they drive on the right every single day? Every day, every minute of every hour of every day, most people are driving on the right side of the road. Why? Pause the video. I'm serious, pause the video. Don't just, I'm waiting for you to hit pause. I think it's the K key for those of you watching on YouTube. You can also do it with the space bar. Pause the video! Welcome back. So why do we drive on the right side of the road instead of the left side of the road? Because it's the law. For this you are paying! It's true. But why is it the law? Why is it the law? Why do we need a law for that? Because there were 2 equilibria. Right? Because there were 2 equilibria. If there weren't multiple equilibria, if there was only one equilibrium, remember, there's no social planar in game theory. So whatever survives Nash equilibrium analysis, whatever survives equilibrium analysis is a possible prediction. And it is a possible prediction because it is what emerges socially out of individual good play. I'm doing what's best for me, you're doing what's best for you. There is nobody saying this is what's happening in society. And what happens is, under complete anarchy, in the absence of a state, either left or right is a possible equilibrium. But if we woke up and we had any vagueness about which equilibrium is the equilibrium we're playing, we're back where we started. We need something to tell us which equilibrium is the equilibrium to play. And that's what the state does. In a very minimal sense, the role of the state is to help us to adjudicate among competing and otherwise equal equilibria. 1-1, it's not like we're creating any winners or losers. It's not like the right is any better than the left or the left is any better than the right. The whole point of driving is to not hit one another and to get where you're going. It doesn't really matter if you drove on the left side or the right side to get there. It's not like people take personal pleasure in saying, oh, I just really enjoy being on the left side of the road as I do this. That isn't true. You like getting where you're going and not being crashed into. So how do we adjudicate among these otherwise completely interchangeable equilibria? The state tells us, drive on the right or else. And you're like, this sounds really, really stupid, but it's not. I'm gonna try to aim better. It's a good book. It's called War in the State. Huh? Apparently now I'm just gonna speak only in grunts. I'm gonna stand up to make sure that, there we go. Oh yeah, look at that. Look at that. So this is chapter 2. Chapter 2, Reason of State. Reason of State. Chapter 2, Reason of State. Why do we have states? Why do we have states? Why do we have states? What is the reason of states? That's a crazy question, right? Why do we have states? We could have landed all sorts of other places. There were competitors. The nation state as we know it wasn't the only way that we ever organized ourselves. We were in city-states, we were in loose polities, we were in fiefdoms, we had all sorts of different ways to organize ourselves. Why do we have states? Why? Well, Wagner tells me, this is the second page of this chapter. And it's got a stupid coordination game in it. It's got a coordination game in it. You're like, maybe this is a stupid book. This is not a stupid book, right? Let's go to the back. Back blurbs. You should never listen to back blurbs of books because this is when people are being especially nice. Nevertheless, you can, okay. So the aforementioned James Fearon, a very well-known international relations theorist, among other things, possibly the most important book on international relations theory since Ken Waltz's Theory of International Politics, which we discussed a few weeks ago. The single most important book in IR theory of the 20th century. This is potentially, according to James Fearon, the most important book in IR theory since then. Maybe. That's high praise. This is one of the best books on IR theory that I have read in a very long time. Robert Powell. It is required reading for any student of modern IR theory. And my favorite, this was one of my teachers that wrote this one. Painting on a vast canvas. Oh, I feel like this needs to be a little bit more like this. Painting on a vast canvas and tackling and integrating topics such as state formation, domestic politics, and international conflict. R. Harrison Wagner's War and the State offers many brilliant insights into the nature of international relations and international conflict. War and the State compellingly highlights the importance of constructing rigorous and valid theorizing and sets a high standard for all students of international relations. The field has much to gain if scholars follow the trail blazed by Wagner in this book. It's a coordination game! Just keep going. Just keep pushing. Just keep coming to class every day. Just keep coming. This stupid scribbling, there's a lot of meaning underneath the scribbling. The reason we have a state is to help us to adjudicate among these equilibria. If there weren't multiple equilibria in this argument, we wouldn't need a state. Whatever was a pure strategy Nash equilibrium would be the thing that we did. It would be the unique equilibrium and it would be what we did, right? Well, let's see about that. Let's think about the prisoner's dilemma. Well, now things get different. So let's think this through. We discussed last week that when we use IESDS on the prisoner's dilemma, we learn, you can probably see the mic now. I moved the mic. I'm too lazy to figure out how to get the shot back to normal. Sorry about that. Obviously, I'm very lazy. So let's see if that plays out in pure strategy Nash equilibrium as well. So let's start from cooperate. We want to give this its best chance. Let's start there. Let's say this is the situation we want. We wish everybody could cooperate. Is this a stable outcome? Okay. Well, conditional on you cooperating, I could defect and go from 3 to 4. And conditional on me cooperating, you could defect and go from 3 to 4. All right, so that's not an equilibrium. Zing, zing. What about cooperate defect? Well, right now I'm getting 1 and you're getting 4. You have no reason to want to defect. You're getting 4. If you defected, you'd switch to 3. That's no good. But if I defected, I'd go from 1 to 2. Similar for defect cooperate. I'm happy getting 4, but you could switch. If you defected, you go from 1 to 2. So none of these are equilibria. The unique pure strategy Nash equilibrium here is defect defect. Why? Well, we're at 2 2. If I defected, I'd go from 2 to 1. And if you defected, you'd go from 2 to 1. So neither of us has a reason to deviate from defect defect. So that's a Nash equilibrium. So this game doesn't have multiple Nash equilibria. Right, there's only one Nash equilibrium. So based on the argument I was just discussing, that means we don't need a state. Well, yes, we do, but not for the same thing. It doesn't help us to coordinate at that point in time. It doesn't help us to picking out equilibrium out of an arbitrarily large set of equilibria. Here, there's only one equilibrium. The role of the state is to make something that was an equilibrium not one anymore. It's to incentivize cooperation. So basically, what I'm saying is two stupid matrices. One with 2 cars and one with a weird suspect. Plus this no deviation idea is enough to tell us 2 competing functions of the state. In one world, it's to say, you know what, we just want to get where we're going. We just kind of want to make sure we can conduct our affairs. It is mutually beneficial for everybody and equally so for us to figure out to just drive on the right side, and that's what we do. Or another country, in England, they just arbitrarily decide to drive on the left side, and that's what they do. But in Prisoner's Dilemma, now we're saying the role of the state, if there is one here, isn't to help us to choose among multiple equilibria. There's only one prediction. There's only one stable outcome. It's to say, well, if you defect, then something bad will happen. We will add costs. We want to incentivize cooperation. We want to tax bad behavior. Something like that. So the role of the state shifts dramatically. Dramatic shift in what the state does. One is a lot more activist and one is a lot more let you guys do what's best for you, but I just want to help you drive on the right side of the road. And in the gray area between helping people drive on the right side of the road and radically shifting their incentives so that they no longer do what's in their individual best interest because we've changed their utility so much, lives a whole lot of different conceptions of the state. But with these stupid scribbles, we just got 2 really compelling characterizations of what states are and what they do. I think that's great. I mean, it's depressing, but it's also great. Here's one final interesting question while we're still here. We don't have a law to tell us to walk on the right side of the sidewalk. We have a law telling us to drive on the right side of the road. There are lots of rules about how to drive. Here are the lanes. Yellow lines versus white lines, dashed lines versus solid lines. Sometimes one lane changes functions. It goes from being like a turn lane to being a one-way. There's all sorts of different rules with driving. With walking, no such thing. So why do we have rules to help us to coordinate on driving on the right side of the road, but we don't have those to help us to coordinate on walking on the right side of the sidewalk? Now here, that's a tough and wrinkled and interesting question. I don't have an answer. I mean, I have hunches. The stakes involved are probably a lot of it. If 2 people walk into one another, that's less of a big deal than if 2 cars crash into one another. It's also easier for us to change our paths while we're walking on the fly. So if I'm walking toward you and you're walking toward me and we're in the same lane of the sidewalk, then it's there's just a slower process. It's not just a matter of swerving. I could slowly adjust my path. Whereas in cars, it's a lot harder to do that, right? So some of it is the stakes, some of it is the speed of adjustment. But wouldn't the world be a little bit more efficient if we had a law that said walk on the right side, the same way that we have a law that says drive on the right side? So why don't we have one? Well, that would be a pretty big imposition. I think that the stakes thing is less like, oh, well, we want to save people from crashing into one another, and more like crashing into one another is bad enough that many people would be willing to invest power into the state to make sure that we avoided it. Whereas walking into one another isn't so high stakes that people are willing to give up the power, the autonomy of how to walk. But this is all just speculation. I really don't know. But I do know that viewing this one stupid problem long enough, the question of Nash equilibrium and coordination versus prisoner's dilemma, suddenly I feel like a different person living in this world that I live in. It's just different. Why do we have states? I don't know. Nobody knows. Nobody knows. Nobody knows. Nobody knows for sure. There are people that work on this. This is an active area of research. Nobody knows. But if you want to get started, you learn coordination games. You're on your way. You're doing a great job. Just keep it up. So, what is the formal definition of a Nash equilibrium? Let's just get this all written down while we can. In order for me to give you a formal definition of a Nash equilibrium, I need to introduce one annoying little piece of notation. So the idea of Nash equilibrium is I'm going to do one thing, holding everybody else fixed. Now with two players, everybody else is rather boring. It's just the other player. However, it might be, as you'll see in your problem set with a voting game, it might be that we need to think about all other voters. Maybe there's 2 other voters or 99 other voters if I'm in the Senate. How do I write down everybody else's actions other than me? Okay, so remember that an action profile is just A equals A1, A2, A3, ... AN-2, AN-1, AN. So there's N choices, 1 for every player, all right? So there's 2 players, it's just 2 choices, left, right. Defect, cooperate, straight, swerve, straight, straight, whatever it is, all right? So it's a vector of 2 choices, 1 for every player. In that case, there's only 2. With N players, it's all of them. I want to be able to write this, I want to write the same thing as player I's choice and then everybody else's choices. I want to be able to say, think about player I separately. Let's evaluate player I separately, all right? So right now, this is an element of a gigantic Cartesian product, capital A1 times capital A2 times capital A3 times ... times capital AN-2 times capital AN-1 times capital AN, all right? So I basically need to pull out the AI parts. So I'm going to write A sub minus I. This is a mild abusive notation. A sub minus I. This is my notation for that action profile taking player I out of it. So hold everything else fixed. Hold all the other choices fixed. All right? So this is everything that's in A except for AI. What do I mean? Well, I'm going to write it out like this. A1, A2, A3, ... AI minus 1. So I get up to the person just ahead of player I in line. AI minus 1, comma, AI plus 1. I jump over AI. I go from AI minus 1 to AI plus 1. I skip player I, and then ... to the end. So now I have N minus 1 choices in a profile, and this profile is officially profile A taking the ith coordinate out of it, taking player I's choice out of it. And that's part of A1 times A2 times A3 times ... times AI minus 1 times AI plus 1 times ... times AN. So that's everybody else. So then if I want to write A, and I want to really pay special attention to player I's choice, I can write A equals AI, A minus I. And that means it's player I's choice and then everybody else's choices. This is what's going to allow us to say hold everybody else fixed. You'll see what I mean in just a moment. So pure strategy Nash equilibrium is something that is imposed on a game. So let me just write out what an N player game is again, just to keep ourselves all in the same space. So an N player game is 3 things. A set of players, capital N, maybe it's 1 ... little n. For every player, there's an action set, capital A sub I. I can go left or right. You can go Bach or Stravinsky. And then for every player, a utility function that reads in a profile of choices. It reads in the Cartesian product of all those action sets, and it spits out a happiness number. So I get to work with that. Let's just put that over my shoulder. So that's still there. And then, so what I'm saying is, we say that a strategy profile, A1, A2, A3, ... AN. So this is something that occurs for a whole profile. It's a whole profile. IESDS was like player by player. This is a whole profile. The whole is more than the sum of its parts. So we say that this is a pure strategy Nash equilibrium if for every player I in N, so for every individual, that player's utility for playing AI against A minus I, right? So that's right here. That player's utility for playing AI, for choosing the candidate equilibrium action against everybody else's candidate equilibrium action. So I play AI against your AIs. What I'm saying is that number must be greater than or equal to UI of AI prime A minus I just spit all over my microphone, for all AI prime in capital AI. So what I'm saying is, this utility that has to be greater than is the utility that I'm getting at this candidate profile, A. So what the idea here is, I can't have a profitable deviation by switching to some other AI prime, some other choice I could have made, AI prime. If I was at defect, it can't be the case that I would do better if I went to cooperate. It has to be the case that what I'm doing is as well as I could do holding everybody else fixed. That's what this A minus I thing means. Notice that it's the same A minus I on both sides of the equation, right? So the only thing that's changing is player I's choice. They're potentially deviating from AI to AI prime, and what I'm saying is, it's a Nash equilibrium if nobody wants to do that. So that's a pure strategy Nash equilibrium. It means that nobody wants to move from where we are, holding everybody else fixed. It really takes advantage of the whole profile. It's no longer do what's best for you, because what's best for you depends on everybody else. Now it's imagine one situation and check to see if anybody wants to move. So this really plays up the fact that Nash equilibrium is a stability concern, right? So you can imagine oscillatory behavior in the world as the following. We're at one profile of everybody's choices. Everybody's doing something, but somebody wants to deviate, so they deviate. Now we're at another profile. But somebody wants to deviate, so then we're at another profile. But somebody wants to deviate. It might be the same person, it might be a different person. Every time we land somewhere, then if somebody wants to deviate, that can't be, that won't be our prediction, because that isn't what happens, because somebody wanted to leave that state of affairs. If we got to a Nash equilibrium though, then we would stop. Nobody would want to deviate. It's stable in that sense. It's a steady state. If we're thinking about the world progressing as a bunch of little individual deviations, a bunch of little unilateral deviations from a bunch of status quos that are potentially the landing spot, well, then a Nash equilibrium is very much a necessary condition to be a prediction, because otherwise we wouldn't land anywhere long enough. We would never land anywhere. A Nash equilibrium is a potential landing point. One thing that's really interesting is if there are multiple Nash equilibria, then there are multiple potential attractors. There are multiple potential steady states. So if we're playing chicken, right, and we're at the swerve straight, if we're at the straight, and we both just died, except we're going to keep going. Now one of us wants to deviate. Let's say that you deviated. Well, now we're at the one where I went straight and you swerved, then I win. And it's a steady state. I don't want to deviate, you don't want to deviate. But we just as easily could have deviated to the world where I swerved. If we both had swerved, we'd be back in a non-steady state because we both had wished that we had gone straight. So there's all this, the world is just kind of turning until we get to a steady state. That's kind of interesting when you think about it that way. That's why matching pennies is a really useful way to think about pure strategy Nash equilibria. We'll talk about that in the C block and you'll see what I mean. There is no steady state there. Somebody always wants to deviate. But before we get there, I want to observe the fact that evaluating Nash equilibria this way is really tedious, because those Cartesian products can get really big really fast. That's a lot of profiles that we have to check. If we check them all exhaustively, it would take a long time for us on a human level. And even if we program them to a computer, if there was any amount of complexity in the available choices, let's say that it was 2 players and I had 100 choices and you had 100 choices. Right now we've got 100 times 100 choices. It's a lot of different profiles to evaluate. What if it was 1,000? What if it was 10,000? You don't think that there's 10,000 different things? Now that's just with 2 countries. What if there were 200 countries and each could do one of, 5 things? It's 200 to the 5th. That's a huge number. We don't want to evaluate all those profiles. How are we going to find all the Nash equilibria of a game without having to check every one of these flipping profiles? It's so annoying to check every flipping profile. So, Chewy says hi. So how are we going to do that? How do we simplify this and hopefully in a substantively meaningful way? And that's what we're going to talk about in the B block. So let's go to the B block. So the way that we simplify this is by thinking in terms of best response. What do I mean by that? Well, I'm going to introduce a new kind of mapping. It's going to read in what you do, and it's going to spit out the best thing for me. Okay? And that could be everybody. I could I could read in lots of different people's choices and then spit out what's best. Okay? So let's I don't know, what would be a fun one? Let's do assurance. So here's the assurance game. So the logic is very similar. This might look, it's a slightly different way of seeing it. So we're going to think player by player again instead of profile by profile, but it'll just be 2 sides of the same coin. So here we are. Let's think this through on row player's side. So let's think the row player is saying, I need to think through every possible contingency about what column player could do. And I'm going to figure out in advance what would be the best thing that I could do in response. Okay? So, for example, let's say that row player was saying, what would I do if column player was playing cooperate? You could cooperate and get a 4, or you could defect and get a 3. Well, the best thing that you could do in response to cooperate is cooperate. The way that I like to do this is I'll put a little star next to that 4. I'll put a star there to say, this is the best response for the first player in this column. Okay? So I'll just put a little star next to that 4. Similarly, if row player thought that you were going to defect, let's think that through. Well, if I cooperated, I would get 1. And if I defected, I would get 2. My best response is to defect. My best response to your defection is for me to defect as well. So I'm going to put a star on that 2. I just want to highlight the fact that the numbers don't matter. I don't care about the utility numbers. The reason I'm starring the numbers is just to call attention to which row or column I want to be talking about. But remember, the best response to cooperate is cooperate. It's the strategies that we care about, not the utilities. The utilities is just a tool. We don't care about the utilities themselves. They're just a means to an end. Well, let's think this through in terms of column player. If in response to my cooperation, in response to row player's cooperation, you can cooperate and get 4 or defect and get 3. You'd rather cooperate. So I'm going to put a star on that second 4. And if we're in the defect row, well, you could cooperate and get a 1 or defect and get a 2. You would rather defect, so I'll put a star there on that too. So I want to highlight that there are 2 profiles that have everybody with a star. Cooperate, cooperate, I have a star and you have a star. Defect, defect, I have a star and you have a star. This is a mutual best response. Cooperate is a best response to cooperate, which is a best response to cooperate. Which is to say, suppose I was cooperating. If I cooperated, your best response to my cooperation would be to cooperate. And my best response to your cooperation would be for me to be to cooperate, which is what I was doing in the first place. Steady state. Let's say I was defecting. Well, your best response to my defection is to defect. And my best response to your defection that I just deduced is to defect, which is what I was doing in the first place. Steady state. So these are both pure strategy Nash equilibria. You can confirm that nobody has a profitable deviation. Nobody has a profitable unilateral deviation. But it's a little bit easier just to sort of go through the matrix and go ding-a-ding, 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 ding-a-ding. I'm going to put the stars here on all best responses, and anytime everybody has a star, that's a best response. That's a Nash equilibrium. So assurance has multiple equilibria as well, right? We have the nasty one and the happy one, sort of the liberal outcome and the realist outcome. So how would we encode a best response correspondence? Well, that's actually not that hard. So again, I've got this A minus I, this capital A minus I. That's every possible combination of everybody else's strategies other than player I. So that's player 1's choices, player 2's choices, player 3's ... Player I minus 1's choices, player I plus 1's choices ... Player N's choices. So this is every combination of everybody but player I. Okay? So that's going to be the input. And that's going to read in a profile of everybody else, and it's going to spit out one of player I's choices or multiple of player I's choices. So this is a mapping. It's a correspondence. It's allowed to have multiple outputs. It's not one dot, one arrow. It might be one dot, multiple arrows. Okay. So I'm going to say B sub I of A minus I, little a minus I. So it reads in an A minus I, and I'm saying what is player I's best response to everybody else? Okay. What is the set of best things? It's the set of maximal elements where now we're using A sub minus I as like an outside parameter. Okay, so what do I mean by that? Well, it's a set. It's a set of all little a, I, and big AI. So it's a set of all actions that player I could take such that UI of AI A minus I is greater than or equal to UI of AI prime A minus I for all AI prime in AI, in capital AI. So in other words, so it reads in what you're doing, and it says, well, I'm going to think about what you're doing real hard, and I'm going to check my utility numbers on everything that I could do in response to what you're doing. Where you could be one player, you could be two players, you could be many people. Right? So what I'm saying is I'm going to read in what everybody else in the world is doing. And I'm going to spit out the choices that I could make that would maximize my utility function in response to you. Now this looks a little bit hairy. This is a little bit ugly. But it really is just a simple, straightforward set where we just try to find the thing that, conditional on what everybody else is doing, does the best for player I. So I think it's really nice to think about best response correspondences visually. We're going to do this a lot in mixing week next week, so it's good just to get our intuitions honed. So I'm going to put up a boring game. It's a 2-player, 3-action game, just so that we can work through this correspondence a certain way. So here's a game. So row player can go up, middle, down, and column player can go left, center, right. Okay. So what I'm going to do is I'm going to put the row player's actions on this vertical axis. Now there's only 3 things they could do, so I'll put little lines there, but eventually you can imagine a full-on like real line, but up, middle, down. And for column player, it's left, center, right. And so what I'm going to do is I'm going to put each player's best response in this space, right? So if I want to put what is the best response for row player to left, what is the best response for column player to down, and so on, okay? I'll put row players' best responses with big circles and column players with little dots. So let's just think this through item by item. So we'll do row player first. So what is row player's best response if column player played left? Well, their best response is middle. Middle gets them 2. So I'll put a big dot, I'll put a big circle at left middle, or middle left. What is row player's best response to center? Well, it's up. That gets them 2. So I'll put a big dot at up center. What is row player's best response to right? Well, now there's 2 of them, right? They could go up or down, and either would get them 1. There's no rule that says it only can be 1. So here we'll put a big circle for both. We'll put a big circle for right up and a big circle for right down. So these dots, these big dots, represent row players' best responses to each of the column player potentialities. Well, let's think this through for column player. What is column player's best response for row player going up? The best response to up is left. That gets them 2. So I'll put a little dot at up left. What is column player's best response to middle? Well, again, there are 2 this time. They can go left or center. Either one of them gets them 1 happiness point. So I'll put 2 little dots there, one at middle left and one at middle center. And then finally, what's the best response to down? Well, the best response to down is just right. So I'll put a little dot at down right. Now you'll notice that there are 2 instances of intersection of little dots and big dots here. Right? These 2 correspondences intersect twice. Where do they intersect? Well, they intersect at middle left, and they intersect at down right. Well, let's go back to the game. Those happen to be the 2 pure strategy Nash equilibria of this game. There's a direct line that takes this picture and turns it into this matrix and vice versa. It's just that this is a nice way to visualize it. These intersections, where these 2, they don't look like functions to you because you're not used to discrete things, but these are just functions. I'm just drawing multifunctions in discrete space. It's a little bit weird. But where they intersect, where these response curves intersect, is where Nash equilibria happen. That's going to be a really big thing next week, so just be ready for it. All right? The stars might get you through today's problem set, or this week's problem set, but you might need to switch over to this to help understand mixing next week. So now we've seen Nash equilibrium from 2 angles. One is like this steady state across the whole profile thing, right? Where a particular landing spot is a Nash equilibrium if nobody wants to unilaterally deviate. So that sort of starts at the social and then says, well, given a social thing, does any individual want to leave? And this other way of constructing a Nash equilibrium is thinking individual by individual. My best response to you, or my best response to everybody else in society. So what is the best thing that I could do? What is the best thing that you could do in response to everybody else? What is the best thing that Chewy could do in response to everybody else? What is the best thing that Lucy could do in best response to everybody else? What's the best thing that Chancellor Jones could do in best response to everybody else? Individual by individual level, best response. And then we try to see if there's ever a situation where I'm best responding to your best response to my best response. So it's 2... I know it looks the same, and it is the same, but it's 2 completely different animations. One is top down and one is bottom up. Yeah? And I think that the bottom up one is more useful for international relations, right? So for international relations, we think about states under anarchy. We say, these states are going through the world and they're thinking things through and they're saying, what's everybody else going to do and how can I best respond to it? And if we're thinking about a society like domestic politics, it's probably easier to think about the whole profile and say, does anybody want to deviate? You know, and eventually you'll grow comfortable with either option. But I just think it's really cool that this super important workhorse concept of ours, this notion about what aggregated rationality is. Now it's not just individual level rationality. Now it's how do individual level rational agents get aggregated, and not in an Arrow's theorem way. This is more like a how do they generate things with their individual level choices, right? Now, I don't want this to sound super awesome because one thing that they generate is collective action problems. Their individual level incentives generate crappy outcomes, like in the prisoner's dilemma. But sometimes those individual level incentives can generate beautiful outcomes, like in the assurance game, at least the cooperate equilibrium in assurance. And then you wonder, well, how do I make sure that that's the equilibrium that gets played out of the multiple equilibria, cooperate, and defect? Is the solution that you designed to that particular equilibrium selection problem, will it be bottom up or top down? Well, that depends on how you understood it in the first place, doesn't it? That's why you got to see it from every angle, because then when you design a solution, you need to make sure that the solution comports with the underlying problem, the underlying structure of the problem, the underlying logic of the problem. Everybody's got solutions, but do they understand the problem? Why am I skeptical? Because it takes me so long to understand things. Maybe they're just all way smarter. Regardless of whether you think about it top down or bottom up, this stability condition is really interesting. And it's remarkable. This isn't the only way to analyze a game, right? I mean, we could do IESDS. There's all sorts of others. It gets really annoying for me, when people just say, well, here's a game, and so I do the Nash equilibria. And it's like, well, why? I mean, there's all sorts of different ways to see it. Just don't be so mechanical. It's hard because people just want to be mechanical. Isn't it remarkable that the thing that became our workhorse, the thing that became the thing that we teach people how to do by rote, the things that we taught memorizers. I'm okay with memorizers. I like memorizers. The thing that we ended up having to teach them is the thing that was based on no unilateral incentive to deviate. Of all of the things, it could have been other things, but this is the thing that worked best. This is the thing that works best. Of all of the substantive motivations for this being a steady state, Pareto, or some other normative criterion, of all of the things, it's the one that involves this no incentive to deviate. That was Corno's insight. And it's been so routinized, so memorized, so sterilized, that you almost forget that there was something really awesome that happened. Now, somebody just shows you a game and you find the Nash equilibria, like that's what you do. And there's just a lot more to it than that. If you can see this from all the different angles, if you can not be too mechanical with it, it's a real source of beauty and tension and wrinkles. So it's going to turn out that this workhorse approach that we have so far isn't quite enough to get us all the way. We're going to have to extend the logic a little bit, and that'll be next week. But I want to just use the fact that we have maybe 15 more minutes together just to get us ready. I don't want you to be caught completely by surprise when we get to next week. So we need to talk about probabilistic strategy. And we're going to talk about that in the C block. So let's go to the C block. This won't take long. So all that I want to drive home is the fact that row player might not know what column player is going to do. And in fact, row player might know what column player is going to do only in the sense that they think that column player is going to employ probabilistic strategies. What do I mean by that? Well, there's no law that says that you play this game the same way every time. It could be one thing that I could do, even if we were only going to play this game one time, whatever the game is, I could say, well, I'm going to toss a coin, and if it's heads, then I'll go to the left, and if it's tails, I'll go to the right. And that coin could be 50-50, 75-25, 10-90, 1-0, 100-0. That coin has a lot of wiggle room in it. And the fact that the coin has a lot of wiggle room in it is something that we're going to exploit next week. But it is true that it seems to be true. You can't ever quite prove that something is happening probabilistically, but it seems to be true at least that people don't always do the same thing every time. They seem to do things probabilistically. Baseball pitchers don't throw the same pitch every time because they want to keep the hitter guessing. Great generals don't do the same thing on the battlefield every time because they want to keep the enemy guessing. There's actually something to be said for cultivating an image of being somebody that really mixes it up. If I'm at a poker table and I have a reputation for mixing it up all the time, and then I play something, you don't know if I'm playing because I have great cards or because I just mix it up. Apparently this is my hand gesture for somebody that really mixes it up. But what would that look like? How would we encode mixing it up? Well, it's actually going to be pretty straightforward. It'll be easiest if we do this in the context of a game. So actually, I'll introduce a new game that you haven't seen yet that I like a lot for a lot of my examples. It's called Bach or Stravinsky. So Bach or Stravinsky is a coordination game, which is to say we both want to do the same thing. We have similar incentives, but we have somewhat contradictory preferences over what the negotiated outcome is. So here's the story. You and I, we want to watch music together. We don't like to watch music by ourselves. And there are two great concert halls in the Champaign-Urbana area, one in Champaign and one in Urbana. Okay? And so the idea is that we want to drive to the same show, and we don't have cell phones because it's simultaneous move. We want to be at the same show together, but we forget to tell each other where we're going. So then it just comes time to drive to a concert. In Champaign, they're playing a Bach concert, right? And in Urbana, where we're edgier, it's a Stravinsky concert. So we want to watch music together. So we either want to be in the world where we're both at the Bach concert or we're both at the Stravinsky concert. So we want to coordinate. But you like Bach more, and I like Stravinsky more. So you get 2 happiness points at Bach, whereas I only get 1. And I get 2 happiness points at Stravinsky, whereas you only get 1. So now it's a coordination game where it used to be 1-1 and 1-1. Now it's 1-2 and 2-1. But it's the same idea in terms of, oh, here are some zeros, and we want to be on the main diagonal together. Now it's just that there's a bonus for somebody getting a certain outcome that they like. So I like this game because it's sort of like, it adds one little wrinkle, but there's still a lot of zeros, which makes the math easy. You can confirm for yourself that this game has 2 pure strategy Nash equilibria, the one where we both go to Bach and the one where we both go to Stravinsky. If you went to Bach and I went to Stravinsky, wouldn't you wish that you had gone to Stravinsky so we could be musical companions together? Similarly, I wish I had gone to Bach so we could be musical companions together. I'm willing to put up with really boring counterpoint to be with you. Bach is the greatest composer of all time, and it's not particularly close, so I'm just saying Stravinsky because he's edgy, and I want to look really cool. And you're like, maybe stop wearing Mr. Rogers t-shirts. Let's make it easy for the first time. Let's say 1/2, 1/2. So suppose that I thought you were going to Bach half of the time, and I thought you were going to Stravinsky half of the time. Now my life is a lottery. Going to Bach is a lottery. Half of the time you're there, and half of the time you're not. And going to Stravinsky is a lottery. Half of the time you're there and half of the time you're not. It's just like lottery tickets. Except instead of a reward, I get to watch music with you, which is infinitely better than $360,000. Well, what's my expected utility for going to Bach? We haven't talked about expected utility, right? Okay. Well, my expected utility of going to Bach, well, 1/2 of the time, you're at Bach as well, and I get 1 happiness point, so it's 1/2 times 1, plus, well, 1/2 of the time you're at Stravinsky, which means I get 0 happiness points, so it's plus 1/2 times 0, so that just works out to 1/2. So my expected utility for going to Bach, if I thought you were going to Bach half of the time, is 1/2. My expected utility of going to Stravinsky, well, 1/2 of the time you're at Bach and I get 0 happiness points because I'm alone. And 1/2 of the time you're at Stravinsky and I get 2 because I get to listen to all these cool polyrhythms. So 2 times 1/2. So my expected utility of going Stravinsky is 1. So for Bach, 1/2, for Stravinsky, 1. Which means that if I thought that you were going to Bach half of the time, I should go to Stravinsky. Why? Well, I get a bonus. I get a bonus for being a Stravinsky with you. So that half of the time is enough that I still get excited about having a chance to watch Stravinsky and not alone half of the time. Well, let's be a little bit more general now. Suppose that you are going to Bach with probability P and Stravinsky with probability 1 minus P. What's my expected utility? Well, what's my expected utility of going to Bach? Well, with probability P, I get 1 happiness point. So P times 1 plus 1 minus P. With probability 1 minus P, I get 0. So my expected utility of going to Bach is just P. Notice that if P was 1, my expected utility would be 1, which is exactly what I get in that Bach cell. Why? Because if P equals 1, you're not mixing anymore. You're just going to Bach all the time. Similarly, if P was 0, then my expected utility of going to Bach would be 0, which is exactly what I get for being at Bach when you go to Stravinsky all the time. In other words, what we're doing up to this point, what we've done up to this point is just a very special case of this, right? So pure strategies are mixed strategies that are degenerate lotteries, which is to say there are some zeros and ones involved there. So what we did with best responses in stars is going to generalize to probabilities. What's my expected utility of going to Stravinsky? Well, P% of the time, with probability P, I get 0, so nothing doing there. And with probability 1 minus P, I get 2, so my expected utility of going to Stravinsky is 2 minus 2P. Well, then you might be wondering, well, when should I go to Bach versus Stravinsky? Which is to say, when is the expected utility of Bach higher than the expected utility of Stravinsky? Okay. Well, that means when is P greater than or equal to 2 minus 2P? Well, you can work that out, and you should go to Bach if P is greater than or equal to 2/3. So in other words, the only reason I would go to Bach is if I thought you were very likely to go to Bach. Why? Because I get that bonus point at Stravinsky. That bonus point of Stravinsky means that it's not 50-50 that makes me indifferent. Because I'm not really indifferent over these outcomes. I want to be at Stravinsky more than I want to be at Bach. So I'm willing to have some bad outcomes in order for me to get that bonus of the two. So this is going to be the logic that we use moving forward to talk about mixed strategies. Is everybody is creating a lottery for everybody else, and then everybody has to then calculate expected utilities in response to the lotteries that the world is generating for them. And then your lottery has to be a best response to my lottery, and my lottery has to be a best response to your lottery. On the subject, notice that if P was 1, if you were playing Bach for sure, if you were playing a pure strategy of Bach, then I should play Bach because that probability of 1 is greater than 2/3. So my best response to Bach being Bach means that that the expected utility of Bach is higher, not just at 1, but at 2/3 up to 1. Similarly, if your P was 0, so that you were at Stravinsky all the time, well, that's less than 2/3. 0 is less than 2/3, which means I should go to Stravinsky. So my best response to a pure Stravinsky is Stravinsky. My best response to a pure Bach is Bach. But now I've also got my best responses to any of your mixing probabilities that live in the middle. That's pretty interesting, right? We're going to exploit that. That's going to be the space that we live in next week. This is why I wanted to take some time to show it to you now. Is I don't want this to be something that catches you completely off guard. So best response, as we've talked about it, very simple and straightforward, nice to use, and also amenable to generalization, which is a nice perk. Let me give you the final punchline of the week, which will be the reason that you want to do this, and that's the game of matching pennies, which we've talked about so far. So here's the game of matching pennies. Okay. Observe. Let's say we're at heads. I'm happy, I have 1. You're unhappy, you have -1. You could deviate and go from -1 to 1. If conditional on me being at heads, you could go from heads of your -1, you could go to heads tails and get 1. Okay, so let's say we're there now. Because heads is an equilibrium, so now we're at heads tails. Well, you're getting 1 and are happy, but I'm getting -1, and conditional on you playing tails, I could play tails and get 1. So I'll deviate. So heads tails isn't an equilibrium either. So now we're at tails. I'm happy, I have 1. You're unhappy, you have -1. You could deviate. Conditional on me being tails, you could play heads and get 1. So tails is an equilibrium because you want to deviate, and now we're at heads tails. I'm sorry, tails heads. Now we're at tails heads. Well, you're getting 1, so you're happy, but I'm getting -1, and if I deviated, conditional on you being in the heads column, I'd rather be at heads, so none of these are pure strategy Nash equilibria. If somebody handed us the game of matching pennies, which is very important, if somebody handed us the game of matching pennies and said, analyze this, tell me a prediction, we wouldn't be able to with just pure strategy Nash equilibrium. We would come up with 0 predictions, which would be very bad. We wouldn't get paid. So the way that we're going to study games like matching pennies and every other game is going to be with this probabilistic thinking. So this probabilistic thinking is going to be very powerful for us moving forward. None of this is going to matter for your problem set. You could have done your problem set just from the first 2 blocks. I just want to make sure that you're seeing that we're not all the way out of the woods just yet. We have a very nice machine for making predictions, but it's not fail-safe. And it won't ever be fail-safe because there might still be multiple equilibria, which means that we still have indeterminate predictions. However, at the very least, it would be nice if we had at least 1 prediction to show for all this effort. And that's what we'll be talking about next week, so you have that to look forward to. But this very basic logic of Nash equilibrium with the deviations, the unilateral deviations, does anybody want to deviate? What's the whole profile look like? What's the whole societal outcome? and does any individual want to change? If you understand that logic, then I'm quite happy. Right? If you can do this problem set, then I'm really happy. Because this is one of those things that anybody that takes a class like this, what's the Nash equilibrium for two different countries and how they behave with one another? You have to be able to do that for me to feel like I did a good job. That's a necessary condition. So even if this week you don't get it, stick with it. This is a really important part. This is the nitty-gritty. We're at the core of the class. So just keep going, because there's a whole lot of really beautiful insights to follow. What is the state? What does it do? If we can get that just from 4 scribbles, then we're off to a good start, whether it feels that way or not. So just keep pushing. So today we really had a game theory class, right? I mean, we talked last week about how to turn international relations stories into international relations games. What do fables of IR look like? But we never told the ending of any of the stories. And today we talked a little bit about how to get to the ending of the story and be able to say, hey, what actually happens, or what could happen? What satisfies important necessary conditions for what must happen to count as a plausible outcome in international relations? If we're rationalists, then we say that this is a necessary condition that must be lived up to. Non-equilibrium play doesn't make a whole lot of sense, because if there are opportunities to deviate, then a sovereign state equipped with all of the associated privileges and powers would deviate. Now, on the individual level, maybe there isn't quite so much agency, and this is one reason that IR maybe is a uniquely well-suited place to use rationalist-type thinking. However, I think that some of the reason of state stuff that we discussed earlier in today's lecture indicates that there's also a lot of promise about thinking about this at the domestic level as well. And in fact, it's with these domestic problems in mind that I'd like to conclude with a provocative thought. So suppose that you and I had to meet on campus and we didn't have cell phones. We woke up, we knew that we were going to meet tomorrow, but we didn't have cell phones to coordinate, we didn't have email, we didn't have Piazza, we didn't have all these other things. We just had to show up somewhere on campus at some time tomorrow. And if we meet, then we get 1 happiness point apiece, and if we don't meet, then we get 0. So this is a gigantic coordination game. Now it's not just left-right. In a spatial sense, it's David Kinley Hall, South Campanile, Ace's Library, Cranert Center, Illini Union, Alma Mater statue. These are all rows and columns. Think of all the places that we could meet on campus. There's a million of them. I'm not embellishing. Random corner of one of the engineering buildings. Basement of modern languages. Library 4th floor. Library 5th floor. Library 6th floor. There's a million places we could meet on campus. Not to mention time. We could meet at 1 o'clock in the afternoon. We could meet at 6:47 and 39 seconds in the morning. We could meet at 3 in the morning. We could meet at 9:52 at night. We could meet at 3:30 in the afternoon. There's all sorts of different times that we could meet. Now, because of that, there's a whole giant diagonal. We have a kajillion rows and a kajillion columns in a gigantic coordination game called Let's Meet on Campus. And however many rows there are, and columns, it's a square. So however many rows there are that many equilibria. This game has as many equilibria as you would like it to have. Depending on how finely you slice space and time, time is continuous, space is continuous. Depending on how fine you slice things, depending on how much you partition, this game could have an infinite number of equilibria. At minimum, it has a gigantic number of equilibria, all of which are exactly the same from our perspective. We get 1 happiness point no matter what. All we want to do is meet. We don't care where, we don't care when, we just want to meet. We just want to coordinate. So this game has an infinite number of equilibria. So where would we meet? We just ruled out a whole bunch of, by focusing only on equilibria, we ruled out many more profiles than we've included, right? So we're only keeping n, let's say there's n alternatives. If there's n alternatives, you know, here, this place and this time, this place and this time, this place and this time, if there's n alternatives, then there are n equilibria, right? So when it was left and right, there were 2 equilibria. If it was left, center, and right, there'd be 3. So there's however many equilibria there are rows and columns in this giant matrix. But how many elements are there? Well, there's n squared. So we've ruled out n squared minus n. So we've done a great job. We've gotten rid of far more profiles than we've left in. N squared minus n, so long as n is big enough, n squared minus n is way bigger than n. So we've ruled many out, but we still have a gigantic number of possible outcomes. So what would we do? What would you do? Pause the video. No, don't say, I'm saying pause the video and think about it. I can tell you what I would do. I would choose noon. I wouldn't choose 8:17 at night. I wouldn't choose 10:27 in the morning. I'd choose noon. Why? It's easy to remember. Where would I meet? Alma Mater statue. Why? It's easy to remember. Why would I choose some random corner of the computer science building? I wouldn't. I'd meet at the Alma Mater statue. You want to meet me in some random section of Memorial Stadium? That's stupid. Let's meet at the Alma Mater statue. That's easy to remember. Don't make me remember which row and which seat of which section of the stadium we're meeting at. Meet me at the Alma Mater statue. Meet me on the couches of the Illini Union. Some memorable place. We would choose a simple time and a simple place. So there's something deeper than just equilibrium involved with that. Because that simple time and that simple place, noon and Alma Mater, gets us one happiness point together, just the same as every other equilibrium did. It's just that that's the one that's easiest for us to pick out. That's what Tom Schelling called a focal point. One equilibrium out of many equilibria, that's the one that sticks in our head. He was talking about New York City. He said if I had to meet somebody in New York City, I'd choose noon at Grand Central Station. Even though they could meet on the 37th floor of frickin' Empire State Building. At whatever random time you want to choose. Noon at Grand Central Station is the easiest. To remember. Ask your friends. Text some of your friends and be like, hey, if I had to meet you on campus and we didn't know where and when we were going to meet, when would we meet and where? And see what they would say. Now look, it might not, maybe you and your friend have some experience together. Maybe you and your friend go to dinner at Chipotle every day together. So you'd meet at Chipotle at 6. That context can influence the focal point, but you'd still be using a focal point. In the absence of any context, you'd choose noon probably, and one of the easiest to remember places on campus. None of this requires any game theory. None of this requires any game theory. So why have I taught you all this game theory? Why did I talk about this giant matrix with all of the n squared minus n things that we ruled out and all the n things? Would you be able to see it this way without the game to make it so obvious to you that this is a game with a lot of equilibria? Would it have occurred to you that this is a problem? Would it have occurred to you that this is a tricky, wrinkled, nuanced situation? Would it have occurred to you that this is a crisis? Unless you thought about it with this hypothetical fable in your mind. It wouldn't until you were looking for your friend on campus and you didn't have a cell phone. It's tempting to think that all of this math and all of this modeling and all these symbols and all this fancy terminology, it's easy to think that these things are silver bullets and that they solve problems. And many times they do. But what's better about game theory is that it helps us to see problems. It helps us to characterize problems before we're suffering from them. What game theory does, or what a smart user of game theory like Tom Schelling can do, is it gives you a world to talk about something human, like the simplest equilibrium out of a giant set of equilibria. When he did that, he added flesh back to bone. He animated life where once we were talking about sterile, rational robots. But he did so in a principled and rigorous way in the context of a safe, consistent space of game theory. He wouldn't have seen the problem the same way if he hadn't thought about coordination problems. So what this means from the multiple equilibrium thing is that we have many different ways to solve the multiplicity of equilibrium problem. Some of them involve the state, telling us to drive on the right side of the road on the left instead of the left for completely arbitrary reasons just because we want to get where we're going. Some of them involve norms, like walk on the right side of the road. Some of them involve focal points and heuristics, like choose the simplest equilibrium out of many. But regardless, we're talking about adding flesh back to the bone. We're talking about how to see ourselves in this space that we've created. But once we're to multiple equilibria, once we're to indeterminacy, once we're to heuristics or focal points, or even the state, once we're there, then we're engaged in problem solving that is no longer strictly game theoretic. We've taken the math as far as it can take us, and it comes time for us to make principled decisions conditional on the evidence that we have scrupulously and rigorously obtained, or about which we have rigorously theorized. Regardless, we are no longer engaging in the act of science. Instead, we're trying to make the best choices that we can with newfound insight, with newfound awareness of problems that we never would have thought to characterize until we saw them this particular way. Which equilibrium is best may be a matter of sheer pragmatics, or it may be a matter of heuristics, or it may be a matter of culture, or it may be a matter of what the state tells us. But regardless, those things live well outside the realm of all the symbols we've been discussing. And frankly, I suspect that it's naive to think that highly scientific solutions are going to be the only things that emerge out of these interesting and wrinkled and deeply human problems that we experience all the time. All this to say, continue to work on your theoretical muscles. Struggle through these problem sets and learn all you can. Develop yourself. Hone these skills. Get your logic down. But then when the time comes, understand that this can only take you so far. And what comes next, once you've gotten the problem correctly characterized, is going to require so much more of you than what you've pushed yourself through in this class. It's going to require you to have thought deeply about what you care about and what you value. It's going to require you to engage with works of art that make you feel human. It's going to require you to engage with literature that makes you feel like you can learn from one of these characters. It's going to require so much more. But I would argue that this is an important necessary condition too. You must have thought this way at least a little bit of the time. Now, what that proper balance is, no one can say. But what I mean to say is the fact that you're pushing this hard in this one direction means that you're getting so much stronger, but that you have deeper obligations to learn the other things too. It's an act of hubris to think that the solution is going to be clean and tidy and one classable. It will be an act of hubris on your part, but it will more importantly be an act of hubris on mine. So go out there and do your best. Think hard, but think human. And thanks for watching.